Today I'm going to talk about Bloom filters. A Bloom filter is a special data structure that allows us to quickly test whether something might be in a set while using very little memory. Instead of storing the items themselves, it stores a compact pattern of bits. Because of this, it's extremely efficient for large datasets and fast lookups. Throughout this presentation, I'll explain what Bloom filters are, how they work, how they sometimes make mistakes, and where they're commonly used in real-life systems. A Bloom filter is a probabilistic data structure used to check whether an item is in a set. It's considered probabilistic because its results aren't always perfectly certain. It can tell us that an item might be in a set even when it's not. This is called a false positive. However, a Bloom filter will never give a false negative. If it says an item is definitely not in the set, then we can trust that answer completely. This makes Bloom filters very helpful for quickly ruling out items without using much memory. The structure of a Bloom filter is simple. It's just a long array of bits that all start at 0. When we add an item, the Bloom filter uses several hash functions to process that item. Each hash function produces a number that corresponds to a position in the bit array. For every position produced by the hash functions, the filter sets that bit to 1. Later, when we want to find out if an item is present, the filter hashes the item again and checks those same positions. If all of those positions contain bits that are still 1, then the item might be present. Each item is hashed several times. Each hash function points to a position in the bit array, and that position is turned on. Since the Bloom filter only uses bits and not the actual items, multiple different items can end up setting the same bits. This overlap is normal and expected. It's also the reason why false positives can occur. If two items happen to map to some of the same bit positions, the Bloom filter might mistakenly think one of them is present, even if it never was. When checking for membership, meaning if the element is contained in the set, the rules are very simple. If even one of the required bits is 0, then the item was definitely never added. There's no way an item could have been inserted without turning all of its hash positions to 1. On the other hand, if all of the bits are 1, the filter cannot be completely certain. The item might be in the set, but it could also be a collision caused by the other items that happen to share the same bit positions. False positives happen because different items can overlap in the bit array. The more items we add, the more bits become 1. As more bits are turned on, the chance that a new item just happens to match all the required positions increases. However, engineers can mathematically control this. By choosing the size of the bit array, the number of hash functions, and the number of hash functions carefully, we can adjust the false positive rate. If we want a lower chance of a false positive, we simply increase the size of the Bloom filter or increase the number of hash functions. This gives us a good balance between accuracy and memory usage. Bloom filters are especially used in situations where memory is limited but fast lookups are important. This is because they only store bit patterns instead of storing the actual data. They use very little space, even when dealing with millions of items. They also scale extremely well. Adding more items does not slow the system down significantly, and checking membership is always fast because it requires a new hash calculation, only a few new hash calculations, and a few bit lookups. The classic Bloom filter does have some limitations. It only supports adding items, it doesn't support removing them. This is because turning a bit back to 0 would affect every item that used that bit. There are more advanced variations, such as counting Bloom filters that allow deletions, but they require more memory. Additionally, since Bloom filters are probabilistic, they are not suitable for applications where perfect accuracy is required. Any system that cannot tolerate even a small chance of false positive should use a different approach. Bloom filters are used in many systems and technologies. Databases use them to check whether a key might exist before performing slower operations like reading from a disk. This avoids unnecessary work and speeds up performance. Web browsers and security tools use Bloom filters to quickly check if a URL or file might be part of a known blacklist. Large distributed systems such as Google Bigtable, Apache HBase, and Cassandra use Bloom filters to reduce the number of expensive storage lookups. Even networking equipment uses Bloom filters to detect duplicates and manage routing. Any place where we need fast and memory-efficient membership tests is a perfect place for a Bloom filter. In the first graphic, we can see how the Bloom filter behaves when adding and checking items. The row of boxes represents the bit array. At the beginning, all the bits start at 0. In this example, 2 items have been added. The items are ribeye and potato. Each item is hashed several times, and each hash function points to a specific bit in the array. The blue arrow shows the positions where the item ribeye stores its bits. These bits are set to 1. After that, the item potato is added. The yellow arrows show the positions where potato stores its bits. Some of these positions overlap with the bits used by ribeye. This is completely normal. Now imagine we want to check the phrase, "I like ribeye." The Bloom filter hashes the word ribeye again and looks at the same 3 positions. Since all of those positions are set to 1, the filter responds that the item might be set in the set. Ribeye could be present, so this is a possible match. In the second graphic, we're checking a different word. The item is pork chop. The Bloom filter hashes pork chop and points to the positions shown with the purple arrows. When we check those positions in the bit array, we see that one of them is still 0. None of the previously added items ever turns that bit to 1. Because one required bit is 0, the Bloom filter confidently reports that the item is definitely not present. This demonstrates the most important rule of a Bloom filter. If any required bit is 0, the item was never added. Only when all of the bits are 1 do we say that the item might be present. In the third graphic, we check another new item. This item is called lemon. After hashing lemon, the Bloom filter checks the bit positions that lemon maps to. In this example, the 2nd, 5th, and 9th bits are the ones being tested. What makes this example interesting is that all of the bits are already set to 1. However, we never actually added lemon to the Bloom filter. These bits became 1 because they were used earlier by ribeye and potato. Since all the positions are 1, the Bloom filter incorrectly thinks lemon might be in the set even though it is not. This is a classic example of a false positive. It shows how overlapping bit patterns can cause the filter to say maybe even when the item was never stored. The trade-off is why Bloom filters are so efficient. They use extremely little memory and give very fast responses. In exchange, we accept that sometimes the filter says an item might be present when it is not. For many applications, this is an acceptable balance. In summary, Bloom filters are compact, fast, and very effective for huge datasets where occasional false positives are acceptable. They provide quick membership checks, very little memory, and are widely used in real-world systems. Although they cannot guarantee perfect accuracy, they offer a powerful and efficient way to filter and speed up operations in many different environments.